Today we're going to be learning our first lesson with quadratics, but what it's going to teach us is a new way that we can solve a quadratic equation. So a quadratic really means that we have a degree 2 polynomial. And we have worked with lots of quadratics that are in what's called standard form and look like this: ax squared plus bx plus c equals 0. Those are the type of quadratics we have so far been solving and solving by factoring. But we know that it could look like this, just ax squared equals c, where I don't have a linear term in the middle. Or it could look like even this, where I have a single parenthesis squared, right, which means I have that same parenthesis twice, equal to a number of some sort. Okay, so there's all sorts of ways that a degree 2 polynomial could present itself. And so we want to have multiple strategies to solve quadratics depending on what's presented to us. So for example, here's a quadratic. It looks really similar to what we've seen before. So here's a quadratic that's in standard form. It contains a linear term here. One thing, we'll go back to how I know how to approach this problem, I think, after we solve both of these. Right now it's set equal to 0, and I'm going to factor to solve. It's set equal to 0. We know that x squared is going to be x and x, positive c value, so I can place my signs 3 and 1. And I get x equals -3, x equals -1 for my solutions. Okay. When I look at the next quadratic, so if we were in the unit before, if we were in our factoring unit, we see this x squared equals 9. We go, okay, well, I'm going to get it set equal to 0. And I see that it's a binomial, or there's no linear term here. And the only way that I can factor a binomial is if it's a difference of 2 squares, which this is. And it factors into x plus 3, x minus 3. And I get x equals -3 and x equals +3 for my solutions. Okay, so one way that I can solve this quadratic is by factoring. But I can actually solve this quadratic, and probably a little more efficiently, another way. So instead of getting it set equal to 0, what if we just use inverse operations? Excuse me. We know that the square root of x and x squared, okay, that those are inverse operations. If I take the square root of something and square it, that's going to undo that operation, okay, that they're inverse operations. And we've used that before when we were solving, say with the Pythagorean theorem or some of the work we've done previously. We've used the fact that those are inverse operations, just like addition and subtraction are inverse operations, roots and exponents are inverse operations, okay? So to solve for x here, I can just take the square root on both sides of my equation, right? So whatever I do to one side, I need to do to the other. And because these are inverse operations, radicals and exponents are inverse operations, that's going to cancel out my exponent and leave me with just x. Now, what's new here is that we are now solving. So it's not just an expression, and it's also, when we were doing Pythagorean theorem, we were solving for a length. So we only cared about the positive value. But here, now that we're solving, we're going to put plus or minus in front of my answer. And there's my plus or minus here, which I could write separately. I could write as 3 and -3, but many times we shorthand that as plus or minus 3 is my solution. Now, the reason that that is true is because 3 squared gives me 9 and -3 squared gives me 9. So if I'm trying to determine what x could be, well, it could be 3 or it could be -3. And when we're solving and using this inverse operation, using a radical as an inverse operation, when it's a square root, we're always going to have plus or minus in front of my answer. Okay, so here we're using inverse operations versus factoring. Now, let's go back to the first one. The reason we cannot use inverse operations is because we have more, the variable term is in more than one term, appears more than once is really what I should have wrote, is in more than one term in the equation. Okay, meaning I have x squared and I have x. So I can't isolate x because I have that variable term appearing more than once. I can't use inverse operations to solve here. But here I only have x squared. So I can just isolate x because I only have my variable term once. Only one variable term in this equation, okay? So there's a few things that we want to just have written down as some reminders as we work through problems that we could use inverse operations to solve versus factoring to solve that quadratic. So one thing we need to know, inverse operations, that radicals and exponents are inverse operations. Or let me just give us an example. If I have the square root of 3 squared, that's just going to be 3, but these are going to undo each other, right? That's what inverse operations do, is they undo each other. Now, another really important thing we need to know as we work through these problems is when you take the square root of a number to solve, we need plus or minus in front of the value. So that plus or minus is really important. And in fact, it's trickier than just writing plus or minus. You're going to see that in some of our work. So let's look at a few examples of using this to solve instead of factoring. And so many times we want to be strategic in what method we choose to solve a quadratic. So I'm going to show you how I could solve this using factoring. If it was not this unit and we were in the unit before and we were only factoring, what I would need to do for this problem is know that x plus 2 squared is x squared plus 4x plus 4. And then I need to get this set equal to 0 by subtracting 36 and factor it, which would be plus 8 minus 4 to solve. And I get negative 8, positive 4. Doesn't take a crazy amount of time, okay, but is maybe not the most efficient way to go about this problem when it's written in this form. So when I have parentheses squared, or one of the most clearest ways to look for when to use the square root property and when to factor to solve, which really, if you can solve a quadratic, any method, that's great. But we also want to be a little bit intentional in what method we choose. But one way I can know that square root method might be the quickest, most efficient way to solve is when I see that single variable term. So when I look at this equation, I see that x is, I have a single variable in it, so it'll be easy to isolate x. From here, if I want to get rid of the fact that this parentheses is squared, I can take the square root of both sides, inverse operations, right? It gets rid of it. So instead of solving this way, right, this is an option. Instead of solving this way, here's another way we could have solved this quadratic. Take the square root of both sides, gives me x plus 2 equals plus or minus square root of 36 is 6. Okay, so I know when I take a square root, I need plus or minus in front of that value. Now I haven't isolated my variable yet. I need to still subtract 2 from both sides. So then I get x equals -2 plus or minus 6. And this is how I get my two solutions. One solution comes from doing -2 plus 6. And I have -2 minus 6. So it could be positive or -6 here. -2 plus 6 gives me 4. -2 minus 6 gives me -8. Same answers as solving by factoring, different way of getting there. Okay, and let's look at the one underneath here, which is going to be even more involved. And so you're going to see our answer now. Sometimes they're not factorable. So if I had multiplied this problem underneath, this 3r minus 2 squared equals 27, and I had done it set equal to 0, what you would have found is it's not a factorable quadratic. But just because it's not a factorable quadratic doesn't mean there's not a solution. There's a solution, it's just going to not be an integer value like this. It's going to have a radical in it. It's going to not be quite as pretty of an answer. So again, inverse operations. So I can see I only have a single variable term. I'm going to use inverse operations to solve, leaving me with 3r minus 2 equals plus or minus the square root of 27. Now, 27 is not a perfect square, but I still want to simplify this radical. 27 is 9 times 3. So it's going to simplify to 3 square roots of 3. Now, to isolate my variable, to get r by itself, I'd add 2 to both sides. Now I cannot, these are not like terms, so I cannot combine the 2 and the 3 rad 3. So I'm going to leave it as 3r equals 2 plus or minus 3 rad 3. And I can't combine those. They're not like terms as they were up here. I still haven't isolated my variable. I need to divide by 3 to get r by itself. And now I have r equals, I could leave it here, or I can break it apart as 2/3 plus or minus 3 rad 3 over 3. And the benefit of breaking it apart is we can reduce where possible. So 2/3 I can't reduce, but 3 over 3 just cancels out. This gives me 1. So my final answer here is r equals 2/3 plus or minus the square root of 3. And we can't combine those, again, because they're not like rads. Now, if you don't like writing it combined, so this answer is totally acceptable, or I could break this plus or minus apart to show my two answers here. So one answer would be 2/3 plus the square root of 3, and the other answer would be 2/3 minus the square root of 3. Okay, separating it like this. Okay, or I can write it condensed as one solution and plus or minus in the middle. I could add rad 3 or I could subtract rad 3. And there are my two answers. And again, if you're saying to yourself, well, I'll just keep factoring. First of all, not as fast for problems like this. Secondly, for the first one that worked, I could expand it and factor. But here, I can't factor something that these are my solutions, that I have irrational numbers in my solutions. So that factoring is not something we can always rely on. It's something that's a really efficient way to factor many, many quadratics, but not every quadratic is factorable, or not every quadratic is set up for factoring to be the fastest way. Okay, so here we have another quadratic that's set up in a way that inverse operations or square root method is going to be a little more efficient, because I can get rid of this rad by just taking the square root of both sides. And again, so 3x plus 1 equals plus or minus the square root of 18. Now 18 is not a perfect square, but we want to simplify it. It's 9 times 2, so into 3 rad 2. And now I'm just isolating this variable, so subtract 1 from both sides. And just like my last example, I can't combine -1 with my radical, so I'm leaving those separate. And then to get x by itself, I'm dividing by 3, which gives me -1/3 plus or minus 3 rad 2 over 3. And just like my last example, I can't reduce here, but I can reduce 3 over 3 giving me x equals -1/3 plus or minus the square root of 2. Again, I can tell by this answer, this isn't a factorable quadratic, but we can still get our answer by using this other method. Let's look at the last two in this column, and then I'll let you try some on your own. So you'll notice that on our next one, we don't, before we can take the square root or use inverse operations here to get rid of my exponent, I need to isolate, get the parenthesis, if it's this form, alone on the left or right hand side of the equation. So the ones we've done so far, it was already set up like parentheses squared equals blank, parentheses squared equals blank. Here we have some additional things happening along with our parentheses. So first, I'm going to add 180 over. Now I'm set up to just, okay, I can take the square root here. That's going to get rid of that. And I'll take the square root on the other side. So I'm left with just 2x minus 5 on the left-hand side and plus or minus the square root of 180. Square root of 180 can be divided by 36. It's 36 times 5, giving me plus or minus 6 square roots of 5. Okay. Now, isolating this variable, add 5 over, which cannot be combined with that radical. Divide everything by 2. And then I can 5 halves plus or minus, leave this improper fraction. Do not write like a decimal or a mixed number there. Plus or minus 6 rad 5 over 2. And I can reduce this 6 halves. I can't reduce the 5 halves. So give me x equals 5 halves plus or minus 3 square roots of 5. There's my two solutions, still two solutions. I'm just writing it condensed without plus or minus. Now, so when I see an equation like this, really obvious that inverse operations are the way to go, because again, it might not be factorable anyway. So let's go with inverse operations and get the solution, whether it's a factorable quadratic or not. These types of equations, students sometimes miss that they could also use inverse operations. So I could get it set equal to 0, and I could try to factor. Or because I noticed that there's no linear term, so there's only this variable term, I can isolate x, sorry about my dog, by using inverse operations, just like we would a linear equation, right? So I have 61 subtract 7, giving me 54, and then divide that by 2, giving me 27. And now to get just x, I just need to take the square root of both sides, plus or minus the square root of 27. So this wouldn't have been factorable if we had set it equal to 0, because I don't have a perfect square here, giving me 3 rad 3 when I simplify my solution. And I still, again, I have two answers here, positive 3 rad 3, negative 3 rad 3. You could write them separately if you wanted to. You could write it like this. Okay, if you like that better, or I can write that as plus or minus 3 rad 3. So what I'd like you to do is try using inverse operations, square roots to solve the quadratics on the right-hand side of this paper. And then restart the video and see how you did. Okay, let's look at our answers here. So first one, no simplifying needed, but then I need to add 4 over. Here's my two solutions. On the second one, now there's no reducing that happens when we divide by 2. So if you had your answer written like this, 5 plus or minus 3 rad 2 all over 2, that's fine too. So this would be an acceptable way to write that solution, or break it apart so you can see the real and the irrational part. Next one, I have to add 48 over first and simplify it, and we can reduce part of that answer. So breaking it apart brings me to here. And then it switches to a little bit different looking equations, but still with a single variable term. So using inverse operations to isolate that variable. Now we got to talk about this last one. So here's my variable term. If I were to add 3 over, I'd have -2. Divide by 4, giving me -1/2. Can I take a square root of a negative number? So the question you're asking yourself is there a number that multiplied by itself is going to give me a negative? And the answer would be no, because a negative times a negative is going to give me a positive, and a positive times a positive is going to give me a positive. So there is no real number solution to a square root of a negative number. So if I went to go to solve this right here, this negative should be a red flag to me, that there is no solution. There's no real solution. In algebra 2, you would have an imaginary solution here to this, but there's no number that multiplied by itself is going to give me -1/2. So because I cannot take the square root of a negative number. Okay, so if we encounter that in our homework or on a quiz or whatever, we know that's like alarms going off, can't do it, and we just write no real solution. Sometimes they put like no real solution set, they do this. I tend to write my zeros kind of looking like that too, but either one's fine. Right? No real solution there. We cannot take the square root of a negative number. Just keep that in mind in case we encounter it as we work through some problems.